Welcome to the ninth lecture. In this lecture, we'll study high frequency response of amplifiers. Particularly in this lecture, we will study high frequency response of BJT amplifiers. Right. For BJT, we have already studied that there are two junction capacitances which are responsible for a decrease in gain at higher frequencies. This one, this FC, the upper cutoff frequency. This upper cutoff frequency, for this direction in gain, the responsible capacitors are these two, CBC and CBE. These two capacitors are responsible. This CBE is on the input side. It's a small recap. It's on input side, whereas the CBC is between input and output. This is between input and output. So in one of our previous lectures, we solved an expression for which we computed that the CBC, part of it can be thought of as solely on the input side and part of it can be assumed to be on the output side. Right. And that was, after a small proof, we came to the conclusion that CBC, the portion of CBC on the input side is this, CBC times 1 plus AB. We proved that in one of our previous lectures, and the portion that is visible at the output is this 1 plus AV over AV. And we also studied that if AV is large, this ratio gives us a value that is very close to 1, because adding 1 in a very large value divided by a very large value gives us a number that is very close to 1. Right. So the amplifier that we will be analyzing in this would be there is the eraser. Okay. I lost my eraser. So the amplifier that we will be analyzing is this common emitter amplifier with voltage divider biased configuration, with emitter resistor bypassed, so what should be this junction capacitor CBE is on the input side, and part of the CBC, that is 1 plus AV times CBC, is also on input side. So we have two capacitors on input side from the base terminal to ground, and we have this R1, R2 and beta RE. They are also on the input side. So the input circuit is something like this. We have this source and we have this parallel combination of R1 and R2, and we have the CBE from, this is base terminal, and we have another capacitor that is CBC times 1 plus AV, the part of CBC on the input side, and one other resistor that we see by looking into the base terminal, that is beta times small re, the junction capacitance. So this is what is seen at the input. So we can somehow, and of course this source may also have a resistance. Suppose if it has a resistance that we call as RS, and then we can redraw this circuit by replacing these two parallel connected resistors as one. So the same circuit can be drawn such that we remove this beta Re and draw it as one resistor, R1 in parallel with R2 in parallel with beta Re. And we can draw one capacitor instead of having two capacitors in parallel. And we know when two capacitors are in parallel, they are added together. Therefore, CBE plus CBC times 1 plus AV. Now, this is the circuit we have. And what we have to do is we have to find out the voltage drop across this capacitor. And let's call this as C total, across which we have to find the voltage. So this is the load across which we have to find the voltage. So what we have to do is, if you want to find out the voltage drop across CBC, there can be many options, but Thevenin's theorem is the most obvious option. Right. Applying Thevenin's theorem to this circuit, we know the steps are that first of all, the first step of Thevenin's theorem we studied in circuit analysis is applying Thevenin's theorem. So the first step of applying Thevenin's theorem is that we remove load. And if we remove load, we are left with this circuit, this source in series with the source resistance Rs, and then in series with this R1, in parallel with R2, in parallel with beta Re. And we have to find this voltage and we'll call it V Thevenin. So we can straight away find this voltage using VDR, voltage divider rule. So V Thevenin, by applying voltage divider rule, can be R1 in parallel with R2 in parallel with beta Re divided by Rs plus R1 in parallel with R2 in parallel with beta Re. So this is times Vn. So this is the expression for V Thevenin after we have removed this load. And what's next? The next is to find R Thevenin. We know that. And how do we find V Thevenin, R Thevenin? From elementary classes, from circuit analysis, we know that to find R Thevenin, we remove load and we replace sources with their internal impedances. The internal impedance of a voltage source is very small, it's ideally 0. So to find R Thevenin, we replace voltage source with a short circuit, and we have this resistor R1 in parallel with R2 in parallel with beta Re. And we have to find R Thevenin by looking into the circuit from here. So R Thevenin would be this in parallel with this. So R Thevenin is Rs in parallel with R1 in parallel with R2 in parallel with beta Re. So now since we have computed R Thevenin and V Thevenin, now we can draw Thevenin's equivalent. All right, Thevenin's equivalent is this. Now we are ready to draw Thevenin's equivalent circuit for this. For that, we will have this V Thevenin connected as source, R Thevenin in series, that is equal to Rs in parallel with R1 in parallel with R2 in parallel with beta Re, and we'll put the load back, that is this C total. So we will put this load back. And then we have to find the voltage drop across it. That is very simple. To find that, of course, we'll apply VDR. So, and this is also an RC circuit, series RC circuit, and this is a low pass circuit because we are going to compute the voltage, this output voltage across this C. So, and for this circuit, we know that at FCU, we previously know that what happens at cutoff frequency. For an RC circuit, what happens at cutoff frequency? Of course, at FC, and this will be FCU because it's upper, this is not L. If it is a low, if it is a lower cutoff frequency, we call it FCL. But here it is FCU. But we know that at cutoff frequency, XC is the same as R. Here we have R Thevenin, so R Thevenin. Here we have XC total because C is C total, R is R Thevenin. We studied while we were studying low pass frequency response that at FC, XC is the same as R. XC and R are the same. So now we are ready to compute the upper cutoff frequency caused by the input by the junction capacitor, by the equivalent junction capacitors on input side. Right. For that, XC total is R Thevenin, and we know that R Thevenin is R1 in parallel with R2 in parallel with beta RE in parallel with RS. So this is XC total equal to at FCU. So therefore, FCU caused by the equivalent input side capacitances. Therefore, FC upper due to FC upper due to input side capacity, due to the equivalent junction capacitances on input side, not on output side. On input side is 1 over 2 pi R Thevenin, that is R1 in parallel with R2 in parallel with beta RE in parallel with RS times C total, where C total is, we know this is the junction capacitance on input side plus the equivalent junction capacitance between the output and the input. So using this complex operation, we can calculate FCU, but this is due to the equivalent junction capacitances on input side. Right, that's all for this lecture. In the next lecture, we will find FCU, the expression to find FCU due to the equivalent capacitances on output side. But there will be junction capacitance, and we are discussing the upper cutoff frequency. All right, thank you.